The dream is beautiful. Leave Earth, cross the planets, break free from the solar system, reach the stars. For generations, humanity has looked up at the night sky and believed that one day we would simply go. But there is a terrifying truth hidden behind that dream. The moment you try to leave the solar system, space stops being an adventure and starts becoming a death sentence. Beyond the edge of our cosmic neighborhood lies an environment so hostile, so unforgiving, that the greatest threat may not be fuel, engineering, or even distance. It may be your own body. In this video, you will discover why escaping the solar system is far more dangerous than most people realize, why the sun may be the only reason you are alive right now, and why the universe beyond it could slowly destroy the human mind, body, and future in ways science fiction rarely dares to explain. Because leaving our solar system is not just about building a faster spacecraft, it means entering a region of evolution that never prepared you for. A place filled with invisible radiation powerful enough to tear through flesh. Distances so extreme, they break human timescales. Isolation so complete, it could crush psychology. Self and laws of physics that may make human survival nearly impossible. By the end of this video, you will understand why the stars may not simply be far away, they may be biologically forbidden. Welcome to the channel. If you are fascinated by the mysteries of space, physics, and humanity's future, subscribe now, because this journey is about to challenge everything you thought you knew about reaching the cosmos. Since the beginning of civilization, humans have wanted to go farther. First across rivers, then oceans, then continents, then skies. Every frontier we faced seemed impossible until it was not. That pattern shaped our confidence. We crossed the Atlantic. We reached the moon. We sent robots to Mars. So naturally, many assume the next step is obvious. Leave the solar system. Travel to another star. Expand beyond our sun. It sounds like the next chapter in human progress. Movies promised it. Science fiction built entire civilizations around it. Massive starships crossing galaxies. Humans colonizing distant worlds. Interstellar travel became more than science. It became destiny. But destiny can be deceptive because space is not an ocean, and the solar system is not small island chain waiting to be outgrown. Most people think of the solar system as the sun and its planets. Mercury, Venus, Earth, Mars, Jupiter. Pluto, if they still remember it. That mental map is deeply incomplete. The real solar system is not defined only by planets. It is defined by the sun's influence, its gravity, its magnetic dominance, its solar wind, its protective bubble. This giant invisible shield is called the heliosphere, and almost nobody truly understands how important it is. The heliosphere is created by charged particles constantly flowing outward from the sun, forming an enormous protective region that stretches far beyond Pluto. This bubble pushes back against some of the dangerous cosmic radiation coming from interstellar space. In simple terms, the sun is not just a star. It is also a shield. Right now, every second, that shield helps protect life on Earth from parts of the violent galaxy beyond. Without it, survival becomes much harder. And once you leave it, everything changes. This is where science fiction often becomes dangerously misleading. Stories focus on engines, warp drives, cryosleep, alien planets, but real astrophysics asks a far question first. Can your body even survive the journey? Because outside the heliosphere, the galaxy becomes more exposed. Radiation levels rise. Energy particles move through space at near light speeds. DNA damage increases. Cancer risk grows. Neurological damage becomes more likely. And this danger is invisible. No explosion. No dramatic collision. Just silent, relentless biological erosion. A slow attack at the cellular level. And that is only one problem. Distance itself may be even more terrifying. Humans are used to movement on Earth scales. Cars, planes, even rockets, but cosmic distance is something else entirely. Light from the sun takes about 8 minutes to reach Earth. That seems fast, but the nearest star beyond our sun, Proxima Centauri, is over 4 light years away. 4 years at the speed of light. And humans cannot travel anywhere close to that speed. The fastest spacecraft ever built would take tens of thousands of years to get there. Not decades, not centuries, civilizations. This changes everything. A trip beyond the solar system is not like crossing a country. It is more like sending generations into a void where those who begin the mission may never see. Its end. And there is another truth most people ignore. Space is not empty. That idea sounds simple, but it is wrong. Deep space contains radiation, dust, rogue particles, magnetic forces, and psychological horrors created by isolation itself. The farther you go, the less rescue becomes possible. Communication delays stretch. Supply chains vanish. Earth becomes unreachable. At some point, you are not exploring. You are alone, completely. And human beings did not evolve for that. Every part of our biology was shaped by Earth, gravity, atmosphere, magnetic protection, day-night cycles, social contact, natural ecosystems. We are the product of this planet. Even low Earth orbit already harms us. Astronauts lose bone density. Muscle weakens. Vision changes. Immune systems shift. Now extend that not for months, but for decades or generations. The question becomes disturbing. At what point does deep space stop supporting human life and start reshaping it? This is why the true challenge of leaving the solar system may not be spacecraft design. It may be overcoming the limits of human biology itself. Our species dreams of reaching distant stars, but evolution designed us for African pea. Lanes, not interstellar darkness. That mismatch could be fatal. And then comes the biggest obstacle of all. Mortality, human lives are short. The universe is vast. Those two facts may be fundamentally incompatible. Even if we solve propulsion, even if we build radiation shields, even if we create self-sustaining ships, we still face time. A human life may simply be too brief for the distances involved. So the deeper question is no longer just whether humans can leave the solar system. It becomes something even more unsettling. Can humans leave the solar system and still remain human? Because surviving that journey may require cryonics, genetic engineering, artificial intelligence integration, or abandoning biology altogether. The first beings to truly reach another star may not be us, not as we currently exist. That possibility changes the dream. Escaping the solar system may not be humanity's next step. It may be humanity's transformation or its end. For centuries, we looked at the stars as symbols of hope, destinations, freedom. But science reveals a more haunting possibility. The universe beyond our sun may not just be distant. It may be one of the deadliest environments our species could ever face. And the closer we look, the more the dream begins to resemble a test of survival against radiation, time, isolation, and death itself. So before humanity can truly become an interstellar species, we must answer one brutal question. Are we trying to conquer space, or are we trying to survive something we were never meant to enter? Most people believe the solar system ends somewhere around Pluto. That feels logical. Pluto was once called the 9th planet. For decades, it seemed like the final marker, the frozen border, the last stop before true deep space. But that belief is not just wrong. It dramatically underestimates the scale of the sun's kingdom. Pluto is not the edge. In many ways, it is barely the beginning of the outer frontier. Pluto orbits about 3.7 billion miles from the sun on average. That sounds enormous. On Earth, it is almost beyond comprehension. But in cosmic terms, Pluto is still deep inside the sun's domain. Beyond Pluto lies the Kuiper Belt. This is not empty space. It is a massive region filled with icy bodies, dwarf planets, frozen debris, and ancient leftovers from the birth of the solar system. This region stretches for billions of miles. Objects drift in darkness so far from the sun that daylight there feels more like a bright star than a life-giving force. And even beyond the Kuiper Belt, you are still not out. Farther still is the heliopause. This invisible boundary marks the place where the sun's solar wind begins to lose its strength against interstellar space. This is where the protective bubble of the heliosphere starts to fade. Crossing it means entering a more dangerous region shaped less by our star and more by the galaxy itself. That sounds like the true edge. But even that is not really the end of the solar system, because beyond that may lie the Oort cloud. This is where scale becomes almost absurd. The Oort cloud is a theoretical spherical shell of icy objects surrounding the solar system at distances so vast they are difficult to mentally process. Some estimates suggest it stretches nearly a light year from the sun, nearly 1/4 of the way to the nearest star. That means the solar system is not just a neighborhood of planets. It may be an enormous gravitational empire extending trillions of miles into darkness. And this is where human intuition completely fails. Our brains evolved to understand forests, rivers, storms, and mountains, not light years, not cosmic voids, not distances so large that language itself starts to feel broken. This misunderstanding becomes painfully clear when you look at Voyager 1. Launched in 1977, Voyager 1 is one of the greatest engineering achievements in human history. It used gravity assists from giant planets to become the fastest human-made object ever sent into deep space. For decades, it raced outward. It crossed Jupiter, Saturn, the outer planetary realm. And in 2012, after 35 years, Voyager 1 finally crossed the heliopause into interstellar space. That sounds triumphant. But here is the shocking part. Even after all that time, Voyager 1 has traveled only a tiny fraction of the distance needed to reach the Oort cloud. A spacecraft moving faster than almost anything humanity has ever built spent over 3 decades just reaching the beginning of interstellar space. And on the scale of the Milky Way, it has gone almost nowhere. If Voyager 1 were pointed toward the nearest star, it would take over 70,000 years to arrive. Human civilization itself is younger than that. This means our fastest technology is still crawling, not sprinting, not even walking, crawling. The distances are so brutal that reaching the true outer edge of the solar system may require not one mission, but generations. Families born and buried aboard machines, moving through cold darkness. And that terrifying realization changes everything. Leaving Earth is hard. Leaving Mars may one day be possible. But leaving the solar system, truly leaving it, means confronting a scale so enormous that even our boldest dreams may still be thinking far too small. Right now, you are living inside an invisible shield. You cannot see it. You cannot feel it. But every second of your life, it may be helping keep you alive. This shield is not Earth's atmosphere alone. It is something vastly larger. It begins with the sun. Most people think of the sun as heat, light, and gravity, a giant burning star that gives life to Earth. That is true. But the sun is also a cosmic defender. Every moment, the sun blasts streams of charged particles outward in all directions. This flow is called the solar wind. It races through space at incredible speeds, carrying the sun's magnetic influence far beyond the planets. Together, this creates the heliosphere, a colossal magnetic bubble surrounding our solar system. This bubble pushes against part of the dangerous radiation flooding through the galaxy. And that radiation is not harmless. Far from it. Outside our solar system, space is filled with galactic cosmic rays. These are high-energy particles launched by supernova explosions, black holes, and violent cosmic events across the Milky Way. Some travel at nearly the speed of light. They are not like sunlight. They are more like microscopic bullets from deep space, invisible, relentless, and capable of tearing through living tissue. When these particles strike the human body, they can break DNA strands, damage cells, trigger mutations, raise cancer risk. But the danger may go even deeper. Some studies suggest galactic cosmic radiation could damage brain tissue itself, not just the body. The mind. Animal research has shown exposure may impair memory, learning, and decision-making. In other words, the farther you travel into deep space, the greater the chance that space itself could slowly change how you think. This is one of the darkest realities of interstellar travel. A spacecraft may survive. Its passengers may remain alive, but their biology could be under constant invisible assault. And unlike mechanical damage, radiation injury can accumulate silently, month after month, year after year, generation after generation. Even astronauts aboard the International Space Station receive more radiation than people on Earth. And they are still relatively close to home. Earth's magnetic field protects them partially. The heliosphere still surrounds them. Deep space is different. Once you move beyond the sun's protective bubble, exposure rises dramatically. This is where one of humanity's greatest engineering problems emerges. How do you shield life from something that can pass through metal? Traditional spacecraft walls are not enough. Aluminum can block some threats, but high-energy cosmic rays can penetrate deeply. In some cases, when these particles strike shielding material, they can create secondary radiation. A shield can become part of the danger. This creates an almost cruel paradox. Build heavier walls, and you increase mass beyond practical launch limits. Use lighter walls, and passengers absorb more radiation. Even water, one of the better shielding options, adds enormous weight. Magnetic shielding concepts exist. Plasma barriers have been proposed. Underground habitats on planets may help. But for long-term, multi-generational missions through deep space, no perfect solution currently exists. That means a ship leaving the solar system may not simply be traveling through emptiness. It could be carrying human beings through a slow radiation storm lasting decades. Children born aboard such a vessel might spend their entire lives exposed to dangers no human nervous system evolved to handle. This is not dramatic fiction. This is a real biological obstacle, and it forces an unsettling question. When humanity dreams of crossing interstellar space, are we planning a journey or entering a slow-motion experiment where the galaxy itself becomes the predator? Because beyond the warmth of our sun, survival may depend not just on speed, but on whether fragile human cells can endure a universe filled with invisible fire. Space does not need to kill you quickly to defeat you. It can do something far more disturbing. It can slowly reshape you. On Earth, your body exists in a perfect biological system built over millions of years. Gravity pulls on your muscles. Gravity strengthens your bones. Gravity helps so your heart pumps blood efficiently. Gravity influences balance, movement, and even how fluids distribute through your body. Remove that force, and the human body begins to change almost immediately. This is one of the least understood horrors of deep space. In microgravity, muscles start weakening within days. Without constant resistance, the body begins conserving energy by breaking down tissue it no longer thinks it needs. Astronauts exercise intensely on the International Space Station for hours every day and still lose muscle mass. Bones suffer even more. In space, astronauts can lose bone density at rates far faster than elderly people with osteoporosis on Earth. Calcium leaves the skeleton. Bones become weaker. Fracture risk rises. And this is during missions lasting months, not decades, not lifetimes. Then comes the heart. On Earth, gravity forces the cardiovascular system to work harder. In microgravity, the heart can gradually weaken because pumping blood becomes easier. That may sound harmless until a weakened cardiovascular system must suddenly function under gravity again. Some astronauts return with dizziness, low blood pressure, or difficulty standing. Now, extend this across generations. A child born in deep space may develop in an environment where gravity never properly shaped bones, muscles, or circulation at all. That raises a chilling possibility. Would they even survive on Earth or on another planet? Then there is vision. One lesser-known issue discovered in astronauts is something called spaceflight-associated neuronuclear syndrome. In simple terms, long-term space exposure can physically alter the eyes and brain. Fluid shifts in microgravity may increase pressure in the skull. Vision can blur. Eye shape can change. For some astronauts, these effects can last long after returning home, and scientists are still trying to understand the full danger. The immune system also appears to weaken in space. Certain immune responses become less effective. Dormant viruses can reactivate. Bacteria may even behave differently in microgravity. A spacecraft carrying humans for generations may not just be a vehicle. It may become a biological pressure cooker, a closed ecosystem, limited medicine, limited genetic diversity, no true emergency evacuation. And that creates another terrifying challenge. Reproduction. Humanity often assumes colonizing. Deep space means families, children, and future generations aboard starships. But here is the truth. We still do not fully know how human reproduction functions over generations in deep space. How would embryos develop in microgravity? How would radiation affect fertility? Would pregnancy become more dangerous? Would infant development suffer? Could mutations accumulate? No one has real long-term answers. And without those answers, the dream of generation ships becomes far more uncertain. Small, isolated populations also face genetic bottlenecks. With limited gene pools, harmful mutations can spread more easily. Biological diversity could shrink. Over centuries, this may create irreversible health decline. This means the first true interstellar mission may not just be an engineering challenge. It may become an evolutionary gamble. A drifting human population slowly adapting or deteriorating in ways no one can fully predict. And this leads to one of the strangest possibilities of all. The descendants of humans who leave Earth may still carry our name, but after enough generations in deep space, altered by radiation, microgravity, isolation, and artificial environments, they may no longer be biologically equipped for the world that created them. The journey to the stars may not simply test whether humans can survive space. It may test how much of humanity can be lost before survival itself becomes something else entirely. The human body is not the only thing space can break. The mind may fracture first. On Earth, even in the most remote places, there is usually an anchor, a horizon, a nation, a rescue system, a culture, other people living normal lives under the same sky. Deep space strips those anchors away. The farther humans travel from Earth, the more they leave behind not just a planet, but the entire psychological framework our species evolved around. Astronauts in low Earth orbit already report isolation, confinement stress, sleep disruption, emotional fatigue, and cognitive strain. And they are still close enough to see Earth. That blue sphere in the window matters more than most people realize. It is not just scenery, it is reassurance. Home, a reminder that life, family, and civilization still exist nearby, but once Earth becomes a fading dot or disappears entirely, something changes. The mission stops feeling like exploration and starts feeling like exile. This is where distance becomes psychological violence. On Mars, communication delays with Earth can already stretch from several minutes to nearly half an hour round trip. That means no real-time conversation, no immediate emotional support, no instant crisis management. Every message becomes a delayed echo. Now push that farther to the outer solar system, to interstellar space. At some point, messages may take years. A child could ask a question and become an adult before hearing the reply. A parent on Earth could die long before their words arrive. Civilization itself becomes temporally disconnected. This is not loneliness in the normal sense. It is something more extreme, a complete severing of shared human time. And then comes the brutal reality of rescue. In deep space, there may be none. A failed system, a disease outbreak, a psychological crisis, a violent social conflict, no emergency return, no supply mission, no outside intervention. Every problem stays on board, contained, growing. A starship may become less like a vessel and more like a sealed civilization under permanent pressure. This raises one of the darkest questions in all of Interstellar. What happens to the generations born aboard? A child born on a generational ship did not choose exploration. They did not volunteer. They inherit a mission designed by ancestors long dead. Their entire life may unfold inside metal walls, artificial systems, and endless darkness, all for a destination they may never personally reach. That creates an existential burden unlike anything in human history. Purpose may erode, resentment may grow, social divisions may deepen. Some may remain loyal to the mission. Others may reject it entirely. Over generations, belief systems could split. Cultures could drift. The original purpose of the voyage might be forgotten, distorted, or transformed into mythology. The ship's descendants may no longer see themselves as explorers. They may see themselves as prisoners or something entirely separate from Earth. Psychologists already know that confined environments can intensify conflict, paranoia, depression, and social instability. Now, apply that not for months, but centuries. A closed society with limited space, limited privacy, finite resources, and no escape. Even small cultural fractures could become catastrophic. Mutiny, class systems, authoritarian control, population conflict, loss of scientific knowledge. The threat is not just sadness, it is civilizational decay, because survival in deep space may depend not only on oxygen and food, but on preserving meaning itself. Without purpose, missions fail. Without shared belief, systems collapse. Without psychological resilience, technology alone may not matter. The cruelest part is that deep space may not need to physically destroy humans to end the mission. It may simply wait for despair, disconnection, or generational drift to unravel the will to continue. And in that silent darkness between stars, the first true casualty may not be the body, but the reason for going at all. Even if humanity solves radiation, even if biology adapts, even if the mind endures, there is still one force that may be even more unforgiving: physics itself. This is where interstellar dreams collide with the raw architecture of reality. The universe is not just big. It is structured in ways that make crossing it brutally difficult. For most of human history, speed solved distance. Faster ships crossed oceans. Faster planes crossed continents. Faster rockets reached orbit. So instinct tells us the same pattern should continue. Build a better engine. Go faster. Reach the stars. But space is not scaling the way human history did. Chemical rockets, the technology that took humans to the moon, are astonishing and deeply inadequate for interstellar travel. They burn fuel by chemical reaction, powerful by Earth standards, pathetically slow by cosmic standards. The Apollo missions reached speeds that seemed extraordinary, but at those velocities, reaching the nearest star system would still take tens of thousands of years, not because engineers failed, because chemistry itself has limits. Fuel becomes mass. Mass requires more fuel. More fuel adds more mass. This creates a brutal equation called the tyranny of the rocket equation. To go much faster, spacecraft rapidly become impractical. So true interstellar travel pushes toward relativistic speeds, a significant fraction of the speed of light. And here, energy demands become almost monstrous. Accelerating even a modest spacecraft to a fraction of light speed would require energy on scales rivaling nations or worse. The closer you get to light speed, the harder acceleration becomes. Not just technologically, physically. A core. Ding to relativity, massonorgy. If fast energy requirements rise enormously, the speed of light is not just fast, it is a wall built into reality. Then comes one of the lesser known nightmares of high-speed travel: dust. Not asteroids, not planets, dust. Space contains tiny particles, atoms, microscopic debris, grains smaller than sand, at everyday speeds, harmless, at relativistic speeds, devastating. A tiny speck impacting a spacecraft at a large fraction of light speed could release explosive energy comparable to powerful weapons. One grain, one collision, potentially catastrophic damage. This means deep space ships may need shielding not just from radiation, but from ordinary matter itself. The faster you go, the deadlier the universe becomes. Then there is time dilation. This is often presented as a solution. Travel near light speed and time slows for those aboard. From the crew's perspective, distant stars may become reachable within a lifetime. That part is scientifically real. But there is a darker side. Time dilation protects subjective travel time, not biological vulnerability. Radiation still matters. Acceleration forces still matter. Mechanical failure still matters. Psychology section, all matters. And while travelers may age more slowly, Earth could age by centuries or millennia. The destination may be reachable, but everything you knew could already be gone. Then come humanity's proposed breakthroughs: fusion engines, antimatter drives, laser-pushed light sails. These concepts are powerful. Some are scientifically plausible, but all face staggering barriers. Fusion remains extremely difficult to control. Antimatter is absurdly expensive and dangerously unstable. Light sails require immense infrastructure and precision over astronomical distances. None currently solve every problem. They shift obstacles. They do not erase them. This is why interstellar travel may be more than an engineering challenge. It may reveal something deeper, that biological creatures evolved on planets may simply not be naturally suited for crossing the galaxy. Fish evolved for water, birds for air, humans for Earth. The stars may technically be reachable, but the universe may have built extraordinary resistance into every step: distance, energy, radiation, time, impact, isolation. It is almost as if reality itself demands a price so extreme that ordinary human life may never pay it eoncé. Hanged, at some point, every dream of leaving the solar system collides with one final enemy. Not distance, not radiation, not fuel, death. This may be the hardest truth of all. Human beings do not just need a ship powerful enough to cross interstellar space. They need lives long enough to matter during the crossing. And under everything science currently understands, that may be one of the greatest barriers ever faced. The nearest stars are unimaginably far. Even if technology improves dramatically, many realistic missions may still take decades, centuries, or longer. That changes the mission completely. A voyage beyond the solar system may not be a journey in the traditional sense. It may be a one-way departure from everything familiar. For many travelers, launch could also mean goodbye forever. No return, no reunion, no witnessing arrival. Only faith that descendants, machines, or future minds continue the path. This is where death stops being an accident to avoid and becomes part of the mission design itself. Generation ships are one proposed answer. Massive vessels carrying multiple generations across centuries. The original crew begins the journey. Their children inherit I. Their grandchildren continue it. The founders die long before the destination is reached. This sounds visionary, but hidden inside is something deeply unsettling. Success depends on accepting personal mortality as infrastructure. The mission survives. The individual does not. And this creates a disturbing philosophical shift. The goal is no longer survival of you. It becomes survival of the mission through you. This forces science into territory that sounds almost spiritual. How do you preserve identity across impossible distances? Is a civilization enough, or must consciousness itself survive? This is why aging becomes more than biology. It becomes engineering. If human lifespans remain limited, interstellar travel may demand radical alternatives. Cryonics is one possibility. Freeze the body or brain for future revival. But this remains uncertain, technologically fragile, and biologically unresolved. Then comes suspended animation, artificial hibernation, a slowed metabolic state, still largely experimental. Then the ideas become even stranger. Mind uploading, digital consciousness, transferring memory or identity into machines. If consciousness could be preserved digitally, perhaps humans could cross stars as information rather than flesh. But this creates another terrifying question. Is a digital copy still you, or merely a replica carrying your memories? The body may perish. The pattern continues. Is that survival or replacement? Artificial intelligence may bypass biology entirely. Machines do not age like humans. They do not need oxygen, food, or psychological comfort in the same way. An AI probe carrying human knowledge may reach distant stars far more realistically than biological explorers. But then humanity faces an uncomfortable possibility. The first true interstellar species may not be human beings. It may be human-created intelligence. Our legacy, not our bodies. And then comes post-human evolution, genetic engineering, cybernetic enhancement, radiation-resistant biology, extended lifespans, space-adapted descendants. To survive deep space, humanity may eventually redesign itself, but each modification raises the same haunting issue. At what point does adaptation become transformation? At what point does preserving humanity require changing it so profoundly that what arrives among the stars is no longer recognizably human? This may be the ultimate paradox. We dream of escaping extinction, of preserving consciousness, of carrying humanity into the cosmos. But the deeper science goes, the stranger the cost appears. Leaving the solar system may require surrendering the very biological, psychological, and mortal framework that defines us now. The stars may be reachable, but perhaps only by versions of us willing to sacrifice earthborn humanity for something new, something built not merely to survive the universe, but to become compatible with it. The dream of leaving the solar system has always sounded like the next step in human progress, a natural expansion, a future where we simply build better engines and move farther out into space. But the deeper we look into science, the more that dream changes shape. It stops being a story about travel and becomes a confrontation with reality itself. Because space is not just far away. It is not just empty. It is structured in a way that is deeply hostile to human life. Radiation that can break DNA. Distances that stretch beyond human timescale. Physics that punishes speed with danger. Biology that weakens outside Earth's gravity. And psychology that struggles in isolati, on without end. Every layer of exploration reveals another limit. Not one problem, many overlapping barriers that all point to the same truth. Leaving the solar system is not simply about building a faster spacecraft. It is a survival paradox. To go farther, humans may need to change what it means to be human. Longer lifespans, artificial support systems, genetic adaptation, even merging with machines or transferring consciousness into digital form. Each solution brings progress, but each one also moves humanity further away from its original form. And that raises a question that science alone cannot easily answer. Is the goal to reach the stars as we are now, or to ensure something of us reaches them in any form at all? The universe does not seem designed for fragile biological explorers. It does not stop for evolution. It does not adjust for human limits. It simply is vast, cold, relentless. And yet, the desire to go still remains. That desire may be one of the most powerful traits of our species. But it may also be the reason we eventually have to transform. The stars may be reachable, but perhaps not by the beings who first looked up and dreamed of touching them. If this journal, Arne into the Limits of Space and Survival, made you think differently about our place in the universe, consider liking the video and subscribing to the channel. There is much more to uncover about what lies beyond our solar system and what it may demand from us in return.